In this video, I want to talk about two other symbols that sometimes appear in truth table, namely x's and z's. So before I do that, I want to introduce a circuit which is called a priority circuit, and see how we can introduce some additional symbols to simplify our truth table. So here is an example of a priority circuit. We have a set of inputs. Here we have 4 inputs and we have 4 outputs. So 4 inputs and 4 outputs. The outputs are listed as A3, A2, A1 and A0, and the outputs are Y3, Y2, Y1 and Y0. So just from knowing that we have 4 inputs, what we can do is that we can create a list of all the possible combinations that we can have using these 4 inputs. So I have put them in order from A3 to A0, and as you can see, if I consider this as a 4-bit binary number, this is equivalent to 0 in base 10. The next one is equivalent to 1 in base 10, right? All the way to the last one, which is 15 in base 10. So as you can see, I put all the possible combinations in order, and this way it is much easier for me to spot if there are any rows missing. That's why I said that try to remember how to count from 0 to 15 in binary. So now let's just see what is the functionality of a priority circuit. So the priority circuit basically checks whether a bit from the set of inputs with high priority is 1 or not. So for the first row, since none of the bits of the inputs are 1 or true, then the output, all of them are 0. For the next row, we have A3 to be 0, A2 to be 0, A1 to be 0, and A0 to be 1. So between all these 4 inputs, only A0 is 1. And no bit with higher priority. Here priority means higher weight. So if I consider this as a 4-bit binary number, I can say this has a weight of 2 to the 0, this one has a weight of 2 to the 1, this one has a weight of 2 to the 2, and finally this one has a weight of 2 to the 3, right? So I define the priority here depending on these weights. Of course, you can define the priority however you want. So based on this, since A0 is 1 and the rest are 0, the output associated with priority of A0 is going to be 1. Now for the next row, we have A3, A2 and A0 to be 0. In that case, the output associated with priority of A1 is going to be 1. So we have 0, 0, 1, 0. What happens for the fourth row? For the fourth row, A3 and A2 are 0, but we have both A1 and A0 to be 1. So now, in this case, which one of the outputs should be 1? Is it Y1 or Y0 or both? The answer lies in the functionality that we want for the priority circuit. Since we want to have the output associated with the bit with highest priority to be on or to be 1, between the two, Y1 needs to be 1. Why? Because Y0, which is associated with A0, has the lowest priority. So this means that Y1 is 1 now, Y0 is going to be 0. Let's just repeat this for the next row. For the next row, we have Y2 to be 1 based on the previous discussions. For the row after that, we have A2 and A0 to be 1, but since A2 has higher priority than A0, we basically only have Y2 to be 1. The same is true for the next row as well. Between A2 and A1, A2 has higher priority, so the bit associated with that is going to be 1. That is true for the third row as well. Between these three, A2 has the highest priority or the highest weight. So based on that, Y2 is going to be 1 and the rest are going to be 0. So now that we have seen this, what are the outputs for these last 8 rows? In all of them, A3 is going to be 1. So A3 has the highest priority here. It has the highest weight, 2 to the power 3, right? So the values for the other bits do not matter anymore. So then we have 1, 1, 1, 1 for all the rest of the rows of the truth table for Y3, and for Y2, Y1, Y0, the outputs are going to be 0. So this is what is called a priority circuit. And this is the priority circuit, much nicer than what I wrote. But if you look at this circuit, if you look at this truth table, you realize that there are some redundant cases that you don't even have to mention, right? When you say you are giving priority to, let's say, bits from A3 to A0, whenever A3 is 1, the values for A2, A1, and A0 does not matter. Or whenever A3 is 0 but A2 is 1, the values for A1 and A0 do not matter, right? So that is something that you can use, this redundancy, to basically shorten the length of this truth table. So let's just quickly go through the implementation and see how the definition of the priority circuit translates to the implementation too. Of course, you can use the sum of product form for each one of these columns to come up with a Boolean equation. So for example, for Y0, using the sum of product form, you basically have A3 bar, A2 bar, A1 bar, A0. For Y1, if you do that, since you have 2 rows for which the output is 1, you add the min term associated with each one of these rows. So you have A3 bar, A2 bar, A1, and A0 bar, plus A3 bar, A2 bar, A1, and A0. And you can clearly see that these 3 terms are common between the two. So we can have A3 bar, A2 bar, A1 multiplied by A0 bar plus A0. And from the theorems we know that this is equal to 1. Any variable ORed with its complement always results a value of 1. And then you can keep this again. For this one, you have 4 terms, which I am not going to write here. But if you do the simplification using the axioms and theorems, you see that the result is going to be A3 bar, A2, so this is for Y2, and finally for Y3 the result is going to be A3 after doing all the simplifications. So even though it had 8 terms, when you do the simplifications, it all gets simplified to this. And that is how we did the implementation here. We came up with the Boolean equation that represent the relationship between outputs and inputs. And then we use those Boolean equations to do the implementation. Another way was to use the definition of the priority circuit, which basically stated that we want to assert the corresponding output to 1 only for the bit with highest priority. So that means that whenever A3 was 1, Y3 would be 1, right? Y2 is only 1 when A3 is 0. If A3 is 1, Y3 is 1. But for Y2, when A3 is 0 and Y2 is 1, then you have this term. And so on and so forth, right? So this is how we do the implementation. But what about the redundancy? Is there any way that we can reduce the number of rows that we want to have for this truth table? And the answer to that is yes. So this is a reduced version of the truth table. How did we achieve this? By introducing the X symbol. So X symbol here represents don't care. So any value that we don't care about in the truth table, we can represent it with X. That is true for the outputs too. You will see later on too that for some of the functions that we want to have, we don't care about some of the combinations that result to some of the outputs. And that can help us to simplify the functions even more. But for this specific priority circuit, whenever A3 was 1, the value for A2, A1, and A0 didn't matter, right? And that is what this thing is representing. Whenever A3 was 0 and A2 was 1, the values for the bits below A2 didn't matter, right? And that's why we represent them with X's. And the same is true for this one too. So that is one of the use cases of the symbol X. There is another time that we may encounter X, and that is as a result of contention. So what does it mean, contention? When you have a circuit that tries to drive the output to both 1 and 0, you have contention. So basically, you can think of it this way. You have one output, but it is connected to both VDD and ground at the same time. You remember when we used transistors to build logic gates? At any given time, the output was either connected to ground or connected to VDD, but not simultaneously to both, right? If that happens, that is what is called contention. So when that happens, the actual value or the actual voltage of the output is somewhere in between, right? You may even break the gate too, right? Break the circuit too. It can be 0 or 1 or in a forbidden zone. And this value can change with voltage, temperature over time because of the noise, and usually causes excessive power dissipation that can heat up the circuit and possibly break it. So it is always good to avoid that. So one example, you can see it here. that we have A equal 1, B equal 0, A goes through one inverter, so that makes the output here to be 0, and B goes through another inverter, that makes the output to be 1, and now Y is not clearly specified, because from this path it is connected to 0, from this path it's connected to 1, and that is what we call contention. There are cases that you have contentions in your circuit or in the final implementation that you didn't intend for as a result of a bug in the code or the implementation. And also some other thing that you notice is that we used X for both don't cares and contention, right? So to be able to distinguish them apart, you should add the context. If you are looking at truth tables, they are mainly don't cares if you see X's, right? But if you are looking at the implementation, hardware implementations of your circuit, that is mainly as a result of contention. So there is another symbol that sometimes appear in digital logic circuit, and that is the symbol Z. Symbol Z has several names. We can either call it floating or high impedance or open or high Z. Basically, it is the state of an output in which it looks as if it is not connected anywhere. So the floating output might be 0 or 1 or somewhere in between. But the voltmeter won't indicate whether a node is floating or not, right? So just by the fact of you connecting a voltmeter to that output, you basically apply some load, which kind of defeats the purpose of the high impedance or like the floating Z. One example of such a case is in tri-state buffers. So you remember we had this regular buffer in which we had A as the input and we had A at the output, right? So this is the regular buffer. We can have a tri-state buffer in which we have this input A, we have this output Y, and then we have this additional input, which we usually call it the enable signal, which determines whether this buffer is even on or off, right? So in effect, it's a switch for this specific buffer. So when E is 0, that means that this buffer is not even on. No matter what is the value for A, the output is Z, right? So when this buffer is off, that means that this output is not connected anywhere inside the circuit, right? Conceptually. But as soon as you make the enable signal 1 or turn on the buffer, now whatever you have for A, you can see it in Y, right? So here there was no path between A and Y because the buffer was off. It wasn't even enabled. But when you have the enable signal to be 1, you turn on the buffer. Now whatever you have in A, you can have in Y. You can have a tri-state not as well, right? The concept works similarly. You can even have a tri-state AND, right? So conceptually there is nothing that can prevent you from having that. When the enable signal is 0, this is completely off, the output is high Z, when the enable signal is 1, then whatever functionality that you want, you can have it. You can even have a full circuit, right? Whatever is inside, with some inputs, some outputs, to have an enable signal, right? Conceptually, you can have this. As for the implementation, that's a different thing, right? But conceptually, you can have a full circuit with an enable signal. Think of it as your computer, right? If the computer is off, no matter what key you press at the keyboard or how you move your mouse, nothing happens, right? But as soon as the computer is on, now it can accept your inputs. So think of it that way. So a very good example of how these tri-state buses can be used is, these tri-state buffers can be used is in data buses that you can have. So for example, let's just assume you have this computer, right, which has a processor, right, and then you have several components that are connected to it. So you have, let's say, a video card, or like an Ethernet card, or a memory card, right? Each one of them try to share information with the processor, right, or get the data from the processor. But at any given time, only one of them can be active, right? So by using these tri-state buffers, right, we can control whether each one of these components is in the sending data mode or in the receiving data mode, right? So of course, the exact details are more complicated than what we discussed here, but you can get the general idea by doing enables, by using tri-state buffers. Basically, if this this video card, let's say, if it's in high Z state, that means that this connection is basically up in the air. It looks as if nothing is connected here, right? So that means that it doesn't have any effect on the rest of the circuit, or it doesn't have any access to any data that you share it through the bus, right? So generally speaking, tri-state buffers can be used for these purposes. So in this video, I talked about priority circuit, how we can create the truth table for a 4-bit priority circuit. I talked about how we can make implementations of such circuit, either by using the definition directly or by doing sum of product form and then simplification. Based on that, I introduced the concepts of don't care values in the truth tables, which were usually represented by x's. I said that there are other cases that we use the symbol x, and that is as a result of contention, where there are some outputs in your circuit that can be derived to both zeros and one. And then finally, we saw floating high impedance Z symbol and how it can be used, and then tri-state buses that are very useful in practice.